Alright, before we actually jump to the actual topic of this video, there was this little portion that I had missed out in the previous video, and actually by mistake I stopped the recording, then I couldn't restart it. So yeah, this is left out, just a small portion. Alright, so as we have learned while during discussion that mutual inductance of first coil due to second coil can be arrived at using this expression right here, that N1 phi1, this is a flux linkage across first coil, is equal to M12 times I2, right? That's a basic governing expression for mutual inductance or self inductance also. In fact, self inductance, the only difference would be, instead of there will be no numbering N1 phi1, or ones and twos won't be there. It's just be will just be N into phi is equal to L into I, right? Except the symbol is different. We use L for self inductance. Anyway, that's what the topic of this video is, right? We'll get into that in detail later. Let's get back to our this discussion right here. If we differentiate this term, let's see why we'll be differentiating in a minute, but if we differentiate with respect to time, if we differentiate WRT is with respect to time, if we differentiate this with respect to time, we are in fact going to get, what will I get? I don't know, it's just d by dt of N1 phi1 is equal to, I don't think there is any point differentiating mutual inductance because it doesn't depend on time, right? So according to chain rule, I can just keep it out of the differentiation. M12 times d by dt of I2, right? Let's go a step ahead and then find out this term. Wait a minute, this just looks a little familiar to us, right? Doesn't it? Isn't this just rate of change of magnetic flux? But you must be asking, hey, no, come on, that was d phi by dt. Here it is d by dt of N1 phi1. N1 is only going to N1 is only for multiple turns. This term right here is still the total flux linkage, right? And rate of change of flux through any coil, a single coil or multiple coils, is still going to be equal to your EMF. In fact, it will not just be EMF, it will be negative of EMF, because Faraday's law actually says this, that EMF is equal to minus d phi by dt. So yeah, you have here d phi by dt, except the negative sign was missing, so yeah, you'll have a negative sign there. Is then equal to M12 times I2. I'll just be rewriting this again, that EMF is equal to I'm sorry, it's di2 by dt. So it's gonna be di2 divided by dt, and I can in fact just rewrite it like this. So EMF E is equal to minus of M12 times di2 by dt2, dt, right? So this right here, actually this is a very important expression. But before I go ahead and tell you the importance of this expression, let me define something here. Let me try to we have a pretty good idea of how much 1 ohm of resistor is, and we in fact have a good idea of how much of a 1 farad of capacitance is, but we really don't know. And such terms are always defined. I'm trying to in fact define the value of how much is a 1 Henry of inductance is. So I'm trying to define that, and in order to do that, I'm going to use this equation right here. Let me call this equation I don't know, equation 1. So using equation 1, I'll try to define how much is 1 Henry. Alright, let's try to define that. If I take the magnitude, so I'll be getting rid of that negative sign. If I take the magnitude, let's make rate of change of current equal to 1. So let's say somehow I have achieved this, the rate at which the current through the second coil is changing with some difficulty. I've made it to be equal to 1. If I somehow can achieve that and focus only on the magnitude. So if you achieve this, then I can in fact write that M12, its magnitude, is in fact equal to the EMF itself, is going to be equal to, numerically equal to, they are completely different physical quantities. So I'm just saying that their magnitudes will be equal, so they are numerically equal, right? And therefore with all this, we'll try to in a way define or try to define what 1 Henry is, right? So I can maybe write it like this, that the mutual inductance of a coil is numerically equal to the induced EMF, is numerically equal to the induced EMF if, provided you have done this, if the rate of change of current is equal to 1, or just to be a little fancy, is unity, we'll write it like that, is unity, which is equal to 1. And that's how we defined mutual inductance. So mutual inductance in fact is numerically equal to EMF itself when the rate of change of current to the other coil, see I2, rate of change of I2 di2 by dt is equal to 1. Alright, so that's how you define mutual inductance of a coil. Fine. Alright, now for the real discussion, let's try to get an idea of what self-inductance is, right? So you have this single coil. What is self-inductance? Basically, I've tried to give you a little hint in the previous video itself. What basically happens is, we have this governing equation, right? The governing equation which looks something like this, that N phi is equal to Li. Now why am I not writing M? Because this is self-inductance here. So basically, the changing current in a given coil gives rise to changing magnetic flux through the very same coil, and when that happens, that phenomenon we call it as self-inductance, right? So I'll be using this governing equation and try to arrive at the expression for self-inductance L here. All right, and before that we need to actually define, or at least declare in a way, the terms associated with this coil. So, and I have a single coil. All I need to discuss self-inductance is just one coil, right? So let's say the current in the coil is I, and then magnetic field of the coil is B, radius of the coil is R, length of the coil is L, flux associated with the coil is phi. What else do I need? Area of the coil is A. If I'm missing anything, I'll just mention that as we proceed. All right. And number of turns per unit length, yeah, that's very important. Number of turns per unit length is small n. All right. So using these variables, let's try to get the expression for LHS at least, right? So n is the total number of, capital N is going to be total number of turns. Total number of turns is basically number of turns per unit length multiplied by length. Okay, pretty simple. Flux phi, I'm trying to define flux phi now. Flux phi is magnetic field B into area into, I don't really have to worry about cos theta, so it's nothing, is equal to L into I. Alright, seems pretty simple. I can't really do anything about N into L, so that remains N into L, right? Magnetic field B once again is going to be equal to mu naught N into I. See how simple, no need to worry about which variable, which is 1, which is 2, it's just a self-inductance. And area would be area of cross section, like that cross sectional area, and the radius is r, right? So therefore area of cross section will be pi r squared is equal to, in fact, L into I. Notice both sides there is a common term I which will get cancelled, and therefore I will get the expression for self-inductance L as mu naught N into N will be N squared, so mu naught N squared pi r squared times L, and that right there is the expression for self-inductance of a coil, right? Let's see again, does it depend on the things that we said it depends on? What are the things that the inductance should depend on? It should depend on number of turns, it should only then depend on dimensions of the coil, and if at all it should depend on the medium between the coil, right? So let's see, it does actually depends on those things. Number of turns, does it depend on number of turns? Yeah, clearly. Then what else do we have? Dimensions, does it depend on dimensions? Look at this, R and L, they themselves are the dimensions of the coil. And finally, depends on the medium. Does it depend on the medium? Yeah. Right now I had vacuum, so all I got in my expression was mu naught. Later if we put something in there, some sort of material if we use to fill this region, then the extra term will come there. Alright, fine, and that's the expression for self-inductance, and unit again is Henry with a capital H. Is self-inductance. Let's discuss a little bit about self-induction, like how does this work, and maybe try to define the expression for self-induction, right? And in fact I wrote an equation as equation 1 in the previous slide, and I said this is a very important equation, I'll tell you in a minute, right? So together with this I'll mention that. Please pay very extra attention to that part, because this is going to be a defining equation for the next chapter, that is alternating current. So yeah, let me stop over that. Let's get into self-induction. Maybe self-induction basically is us trying to define the expression L, define the term L there, right? So we'll try that. For that I'll be again using this very expression. So N phi is equal to Li, I'll be using that, and we'll see how it goes. So N phi is equal to Li, basic governing equation. If we differentiate this with respect to time, if we do that, I will get on LHS d by dt of N times phi. RHS L anyway is constant, so according to chain rule I can just keep it outside, di by dt. Alright, but this term right here is nothing but negative of EMF, negative of induced EMF according to Faraday's law. So negative EMF is equal to L times di by dt. Now the time for definition, right? So let me try using this expression itself, and in fact, wait a minute, it's about time now that I put this in box, because this is going to play a very great role. I really want to talk more about this, but before we do that, if for the lack of space I'll write just here, if somehow I make di by dt, that is rate of change of current in this coil, equal to 1, if somehow we do that, then in fact the magnitude of self-inductance. See, if this term becomes 1, then L is basically equal to EMF. So magnitude of EMF is basically equal to E, and therefore we define self-inductance like this, that the self-inductance of a coil, the self-inductance of a coil is numerically equal to, it's again numerically equal to, you have to mention that if they ask you the definition. It's not, they're dimensionally very different, these two quantities, right? So yeah, the self-inductance of a coil is numerically equal to the induced EMF if rate of change of current in the same coil is, again let's be fancy here, unity, or you can just write equal to 1, is unity. That's how we define self-inductance. So if you happen to come across the definition, you can just use that. Alright, now for the real discussion, the term here, this right here, listen to this part very carefully, right? Yeah, so before getting into the discussion of inductor, let me recall a little bit about resistors and capacitors, right? And this part is going to be very crucial for the next chapter. Anyway, listen. So if we have a resistor, let's look at this first portion here, below resistor. Let's say you have a resistor of resistance R, and there is a current, constant current I passing through that resistance, right? Then, and A and B are the two ends of the resistor. And in that case, the potential difference between this end and that end is basically going to be equal to IR. This is basically Ohm's law right here, right? So, but yeah, I'm just trying to remind you how often have we used V is equal to IR, right? And it's definitely very important, this expression right here, right? All right. And for capacitor, let's say you have a capacitor of capacitance C. The capacitance of the capacitor is C, and the charge stored in the capacitor at a given time is, let's say, Q, and A and B are the ends of the capacitor. Then potential difference between A and B is in fact defined as Q by C. And how often, once again, have we not used, how often have we used this expression right here, right? And by based on how often you use a given equation, you know that it is going to be immensely important. And now, why is he suddenly, you must be thinking, why is he suddenly saying all the obvious things, right? Why I'm saying the obvious, stating the obvious once again, is because just to remind you once again that how commonly have we have used these equations, this equation right here, this equation right here, and this equation right here. We have used them so often that they have become like a second nature to us. You don't really need me to remind you that. But why I'm doing this is actually to point out the importance of the next equation. And I have in fact seen students forget this, but this, remember, is an expression for potential difference across an inductor. The next equation is going to be potential difference across an inductor. And by showing these two equations, I'm trying to say that this right here is as important as the previous two for any electric circuit, right? But I have seen, for some reasons, I don't know, students tend to forget this. They don't appreciate the importance of this, right? So I'm trying to emphasize this by giving you the previous two examples, by saying that this is as important as the last two. Alright, enough with that now, right? So let's say I have, and this by the way is a symbol for an inductor, a little, a coil. Don't draw it like a resistor, don't draw zigzag lines, draw it more like a spring. That's a symbol for inductor, right? Let's say in this inductor there is a current, except, like I said, if you have a constant current, then there is no point of having an inductor. It's as good as not having an inductor itself, right? So let's say you have a time dependent current which is varying with respect to time. So current in the coil is I of t, right? And inductance of this coil is L. We have already defined how L works out and all that, right? And what all the quantities on which L depends on, right? So let's say you went to shop and you bought an inductor of inductance L henries, and this is the situation. And once again, let's say this end is point A and this end is point B. If you want to write an expression for VA minus VB, in fact this is not going to be correct. I'll just take the magnitude of this. This is actually, there is such a thing called back EMF, which will be in the opposite direction compared to what you would expect. I'll talk about that more later. But let's say you're taking the magnitude. Basically you're trying to find out the potential difference between this, right? So I'll just in fact can write it as V itself is in fact equal to L di by dt. So this is more like your expression for potential difference across a given inductor. That's the expression for potential difference across an inductor, and you have got to remember this expression. And there is a good chance, maybe I'm discouraging you in some way, I don't know, but there is a good chance that you may forget this. Please don't forget that expression, right? So potential difference across an inductor of inductance L, where the current is changing at a rate of di by dt, is V is equal to L times di by dt. That's the expression for potential difference across an inductor. Which end is at higher potential? About that we'll discuss in the next topics, where we'll try to derive the expression for energy stored in an inductor. We'll talk about something, a very nice concept called back EMF over there. Okay, yeah. So I hope that clarifies it. Please remember this expression. All right, thank you. I hope that was of some help. Great. See you in next one.